This video is part 1 on a lecture from section 5.4 of Math 311, a course in linear algebra at Western Illinois University. We're going to be talking about two things. We're going to talk about symmetric matrices, which we're already familiar with, but we're also going to talk about orthogonal diagonalization and how it's related to symmetric matrices. Okay. So this is actually going to be a pretty big deal with some good, nice applications later on. To begin with, before we get into the heavy theory, I want to just do an example where we're going to take the symmetric matrix, and remember, a matrix is symmetric if it's equal to its transpose, right? So, in other words, and this clearly is equal to its own transpose. What I'd like to do is I'd like to diagonalize this if I can. So we're just going to go proceed as we've done before. So to diagonalize this, we need to find the eigenvalues, and to find that, we find the characteristic polynomial. So we get that the determinant of a minus lambda I, which is 3 minus lambda, 1, 1, 3 minus lambda. And taking the determinant, this is 3 minus lambda squared minus 1. And when you multiply this out, you get lambda squared minus 6 lambda plus 9. And then subtract 1. So this becomes lambda squared minus 6 lambda plus 8. And that's the characteristic polynomial. And we don't have to use a quadratic formula. We can factor this. Factors nicely as lambda minus 4 and lambda minus 2. Okay, so the eigenvalues, so setting this equal to 0, we get lambda equals 4 and 2 are the eigenvalues. So now let's go ahead and find the eigenvectors. So if we let lambda equals 4 and plug that in here, we get negative 1, 1, 1, negative 1. And we're trying to find the null space of this matrix. And we easily see that this means that minus x plus y equals 0, or x equals y. So a perfectly good eigenvector would be 1, 1. If we let lambda equals 2, plug that in here, we get 1, 1, 1, 1. Set that equal to 0, we get x plus y equals 0. So x equals negative y, and 1, negative 1 is a perfectly good eigenvector for this. Now, before we go on, we notice that not only are these, we know that these two vectors are linearly independent. We can see that, but we also know that they come from distinct eigenvalues, so they're linearly independent. But you'll also see that they're orthogonal. If you take the dot product of these, you get 0. Okay, and that's no accident. We're going to find out. All right. Now, normally, we can see that this is diagonalizable because the algebraic and geometric multiplicities are equal in both cases. If we wanted to find a matrix P and a matrix D, for P we could just take these vectors to be the columns. But we're going to do one more thing. We are going to normalize these so that these are unit vectors. Okay, we can scale these by their own lengths, and notice that because we're multiplying these by a non-zero constant, that doesn't change their linear independence or it being eigenvectors or them being orthogonal. Okay. So I'm going to replace this one with, we can see the length is 2, so we're going to divide by the square root of 2. So we get 1 over square root of 2, 1 over square root of 2. And the set length of this is square root of 2 again, so this is 1 over square root of 2, negative 1 over square root of 2. Okay? And we're going to let this be our matrix, P. We usually call it P, but in this case we're going to call it Q for a reason you'll see in a moment. So we're going to let Q be 1 over square root 2, 1 over square root 2, 1 over square root 2, negative 1 over square root 2. Okay. And you'll notice, well, why do we do this? Because the numbers look a little uglier than they would have been. Well, we can see this is orthogonal. Okay. Because these new columns now these two columns are form an orthonormal set. Okay, so this is automatically orthogonal, and this means that Q inverse is going to be equal to Q transpose. Okay, so just as before, we would have we normally, if this was just P, we would write AP equals PD, where D is a diagonal matrix. But in this case, we get that AQ is equal to Q times D, where D in this case, this is an eigenvector for 4, this is an eigenvector for 2, so we have 4, 0, 0, 2. Okay. And then multiplying on by Q transpose on the left, on both sides, we get Q transpose AQ equals Q transpose Q D, which is just D. All right. And then if we wanted to flip this, we could take the transpose of both sides, or take the inverse of both sides, or actually we just take the transpose of both sides, and we also get that Q times D times Q transpose is equal to A. Okay. All right, so we have that, yes, this is obviously A is diagonalizable, but we actually have a stronger condition, right? Because we have that we can use an orthogonal matrix. Now let's see, just to okay, so I'll stop there. We could say that in fact A now, this is going to be 1 over square root 2, 1 over square root 2, 1 over square root 2, negative 1 square root 2. D would be 4, 0, 0, 2. And in this case, the transpose is equal to the, we'll see that the transpose is actually equal to itself, because this is clearly a symmetric matrix. Okay, and so this is A, which is still 3, 1, 3, 1, 1, 3. All right. Now we have a special term for it. We're going to come back to this example a little later on, but this is, we have a special term for this. So not only would we say that this means that A is diagonalizable, we have something we say it's orthogonally diagonalizable, meaning that the matrix P that we would usually use, the invertible matrix, in P inverse AP, can be replaced with an orthogonal matrix. Okay, so that brings us to the first definition. We say a square matrix A is orthogonally diagonalizable if Q transpose AQ is equal to D for some orthogonal matrix Q and some diagonal matrix D. Now this means also, of course, if it's orthogonally diagonalizable, that automatically means it's diagonalizable, since Q inverse is going to be equal to Q transpose. Okay. Well, we're going to actually get some more interesting information. We're going to see in just a moment that if it's orthogonally diagonalizable, it has to be symmetric. Okay, that it can't happen. And then we're going to see, we're actually going to show that symmetric matrices and orthogonally diagonal matrices are the same. But we're also going to see that if A is real and symmetric, the eigenvalues of A are real. Well, they were certainly real in our example, because 2 and 4 are real. We're also going to see that if A is a symmetric matrix, then any two eigenvalues corresponding to different eigenvectors are orthogonal. We saw that in our example, right? We saw that our eigenvectors were orthogonal to each other. And then we're going to combine these things together, and we're going to prove this very important theorem called the spectral theorem, which basically says that a matrix is symmetric if and only if it is orthogonally diagonalizable. Again, if it's a real matrix, that is, it's a square real matrix, meaning all the entries are real. Okay. We've been sort of dancing around these complex possibility of complex numbers and complex eigenvalues. Well, we're going to confront them today in this lesson, but it won't be that bad because we're going to. So as long as if something is real and symmetric, then it's orthogonally diagonalizable, and if it's real and orthogonally diagonalizable, then then it has to be symmetric. Okay, so we're going to prove that, and we're going to show some nice consequences of this. I'm going to prove the first fact right now because it's going to be the easiest one. If A is orthogonally diagonalizable, well, then that means that A is going to be going to be equal to Q D Q transpose. Okay, we get that by just taking multiplying by Q on the right, or on the left, and multiplying by Q transpose on the right, and we get this. Okay, so that's A. So let's see what happens if we take A transpose. A transpose is going to be Q D Q transpose, and apply the properties of transpose. This is equal to the transpose of Q transpose times D transpose times Q transpose. And we know the transpose of Q is just Q. If D is a diagonal matrix, it's equal to its transpose because it's symmetric. Okay, and everything outside off the diagonal is 0. So this is D and this is Q transpose. So this is A. Okay, so A is symmetric. Okay, so that was easy. If I was giving an in-class exam, I would ask you to prove this, and hopefully everyone would get it, right? The other 3 results are going to require a little more theory. Okay, this theory, I'm not going to expect you to reproduce these proofs in class, but I want you to understand the proofs and then the individual steps, and then we'll come back and do some more examples. So, see you soon.